Do you know if that person would be teaching it over the summer?
Your civil, I don't think so, because no, he doesn't teach over the summer.
Wasn't here.
The other thing is, have you taken surveying?
Taking it this coming semester.
Right, okay. Yeah, because that's one of those fall spring classes that gets rotated.
Yeah, so they only offer engineering graphics in the fall at U of A.
Uh-huh.
So just seeing if I could get it out of the way before the fall.
Right, no. If anything gets offered over the summer, it'll be statics. But I'd have to teach it, and at the moment, I'm really tired.
Yeah.
I don't know. I wanted to take last summer off, and that was an epic failure. So I'm not sure.
Is that the last summer you had? Was that the 7 week with Tim?
Was it what?
Is that the 7 week with Tim?
No, it was a 5-week statics
Oh, the
course.
5 week, yeah.
But the instructor did not work out, so I ended up teaching a 4-week statics course.
Yeah, Tim was there for that, right?
I don't know.
Yeah, I remember him last summer.
Does Puma do surveying over the summer?
No, you're gonna have to take it in the spring.
My advisor lied.
They do that a lot.
Whoa. No. I have never talked to an advisor the whole time. I'm set to graduate, bro. Do not talk to these guys.
No, just talk to me. So the answer is no, you're gonna want to take it in the spring.
Each way went through it, get you for all the money you have.
But it doesn't last, it won't last all day. Does that make sense? It's a Saturday morning class, right?
Oh, for a survey?
Survey?
Yeah.
Oh,
It's like,
Here, I believe it's a Saturday.
yeah, I thought it was like a 4 or 5 week,
Right.
6-hour Saturday thing.
No, it's all semester, but yeah, it's like 5 hours on Saturday.
Okay.
We just walk around.
So back in the dark ages, when the dinosaurs, we did something called field session. And so that was, we went 10 hours a day for 8 weeks, 5 days a week. And we did tons of labs. Oh.
When I should move, everybody else wants to sit in the front. Why is it class all on this side?
I don't know. It's because I stand here and they know they can see better.
Oh, Xenium. I sent you 2 emails, so go ahead and respond to those.
Okay, so yeah, so there were 2 weeks of surveying, 2 weeks of vacuum system, 2 weeks of machine shop, 2 weeks of
She oversees.
like electronics talking to computers. So,
No.
but yeah, no, surveying will not be, or drafting this summer.
We were gonna.
I don't know, unless, this is the big unless, we're hiring another full-time faculty member. And unless that person wants to maybe start early and has a real good expertise in that, then maybe. But at this point, standing here today, we don't have any summer engineering classes.
Gotcha.
Because last summer was such a disaster. So if I'm not willing to teach it, I'm not even gonna put it on the schedule, is sort of my attitude.
That makes sense.
Yeah, well, I mean, the boat got close to Spanish Town and my phone activated and blew up. So I ended up teaching the class, and then the other thing is, I'm behind this semester is, been challenging for me in a lot of ways. But I came into it exhausted and that didn't help either. And I didn't have any prep done for 220. You can tell them. I think they already know that I'm only like one section ahead of them. Except I only think we have 3 sections left, so I'm one section ahead of them with almost there. So Abram is here.
Yes.
Jordy, you're here. Xenia's here. Tyler is here. Cameron is here. Caleb is here. Jonathan Martinez Lopez, are you virtual?
No, there is only.
Ben, you're here. Natalie is here. Ricardo, are you virtual? Jonathan N, you are virtual. Thomas, you're here. Olivia is here. Alejandro.
So are we gonna finish that problem that we were working on yesterday, or the other day?
What are we gonna finish?
The problem that we were working on the other day?
Yeah, we can finish it. What problem was it?
It was in the lecture you're in right now.
Yeah, we'll go ahead and do it, sure. Oh, that's the wrong class.
You wanna go to Mason?
Diego, oh, Alejandro is here.
Yeah, we like. Yeah, no, we did more. Right?
Nathaniel,
Yep. It's cool.
Jules,
So it's kind of cool.
Aiden,
I didn't see it.
Dallas. Where's Dallas today? Conjure.
He's like, well, I'm gonna drive
Oswald's here today. Isaac. Isaac is online.
I'm dragging.
Cade is here. Alicia. Ian.
Yeah.
David is online. And Scott. And here comes Dallas. We were just commenting on how we were missing you.
Monitor? Did you like?
All right. So we don't have a quiz or anything today. We don't need to answer the attendance question. Attendance is done. So yeah, we're gonna work problems out of this this section here. And I was told, well, you didn't finish one. Is this the one I didn't finish?
Yes.
Yes, okay. So we're gonna work through this one. And then Ben, would you want to work through that homework one?
Yeah, sure.
Which one is it? Oh,
Yeah.
there's Alicia. All right, well, figure what number it is and do you pull stuff offline or out of the book?
It's number 6.101. It's like, I was just confused on that. It's like because normally when we have that slider joint, it's normally like a vertical or horizontal, but now it's at an angle. But what you were talking about explained it. So
Oh, okay.
if you don't want to go over it and go over this stuff, it's okay.
Wait, is it 6.1?
It's 6.101. But that's the problem.
It looks like an A, B, C.
Yeah,
Yeah.
all right. Okay.
It's probably 2 weeks ago, since she's been there, also, like just. Yeah. Rain, no, I was like, the rain, was that Wednesday?
Yeah, but I don't.
I don't know, it was.
We knew this would change. Oh, no, it went up because of Black Friday. No, I got split it off. Camera 6 of it is.
I could take a picture of it and send it to your email.
Yeah.
No, I think I've got it.
Between the seasons.
I've got it. It looks like a triangle and P is, all right. So let me send this to myself. Shh. Let me send this to myself and then we'll go ahead and look at this homework problem. And then we will finish this problem and move into doing our bending and shear moment diagrams.
Yeah.
Second one.
Oh, I did.
Yeah. Yeah, I get it.
Oh, I get it. It's
Oh.
Oh, I think that. And remembering that. NRT. Started MRT equals. Oh, good, good. I really hope I was. I just had that morning my servers.
Yeah, which that's only when it's ideal, right?
Okay, so this is a homework problem out of 6.3. So let's look at this. I told you it was out of 6.3 and it does say for the frame. So we're assuming nothing is moving on this problem, correct? All right, so let's think about the steps we're going to take to solve this problem. What would be the first thing we would need to do?
Reaction.
We're going to want to find those reaction forces. So let's go ahead and do a free body diagram and solve for our reaction forces. Blow this up so I can actually see it. All right, so our free body diagram. Right, gonna look something like this. And then what Ben and I were talking about at the beginning of class or right before class started was we're gonna start by solving the reaction forces. So we're gonna treat this as one unit. So at E, that is a pin connection. So that means we have an EY and we have an EX. At F, we also have a pin connection. So we're going to have an FY and we're going to have an FX. And then we have P, and your number might vary from mine, but P is 1320 kilonewtons. And P is offset from X. All right. So let's go ahead then and walk through this one. Let's go ahead and start by taking a moment, and we're only going to be able to solve part of it, but that's okay. It's going to give us some information to get started on it. Let's go ahead and take a moment about E. All right. And so our moment about E, and we're going to go ahead and set that equal to 0. So my Fy is then going to be off by 1.8 meters. And I'm seeing this is 0.9 here, and that is 0.9 there. And it's going to be turning it, I believe, counterclockwise. So my Fy times 1.8. The 13.2, that's also gonna contribute, isn't it? So that's gonna be pushing clockwise and it's gonna be off. We're gonna have to add all three of these together. So that's gonna be 0.9 plus 0.9 plus 0.3. So that's gonna be then 2.1. So that's gonna be minus 1320 kilonewtons times 2.1 equals 0. Okay, put that into a calculator. I'm seeing Fy equals 15.4 kilonewtons.
Yes.
All right. We can then, if we sum in the y direction, we can then get our EY. So we're going to have EY plus 15.4 minus 13.2 equals 0. So EY is going to end up being a negative 2.2. All right. So this is now going to be pointing, should be pointing down, and it's going 2.2.
You didn't do FX because it's on the line of action, right?
Well, f of x was on the line of action when I took the moment about E. We're also going to run into another situation. So if we sum in the x direction, we are then going to have EX minus FX equals 0. And it wouldn't matter. If I took the moment about F, I was going to have the same problem. All right. And so we're unable then to go through and solve that. All right. So we do have a little bit more information. Now, this is a frame. So what do we do when it's a frame?
We're taking it.
Load is
We're going to explode it. We're going to take it apart. So let's go ahead and do that. Right. So we're then going to have, let's see, BCD, where should we start? I guess it doesn't. So let's go ahead and look at, this is going to be one of our pieces, right? We know EY is going this way at 2.2, right? I do not know EX. Here, I have a pin connection. So this is then going to have a BX and a BY. And then up here, that's A, and that one is going to have, oh, I should have drawn those in tension. So here we're going to then have AY and we're going to have AX, right? So that is our first diagram, so to speak. We take the moment about A. We're not going to get very far, are we? If we look at this one and think about it, because BY, BX, and EY are all going to contribute, right? So we don't get down to one variable, do we? If I take a moment about B, same thing. If I sum forces in Y or X, we're also going to have multiple variables. Does everyone see how we're going to run into trouble? So we need a little bit more information than to be able to solve this particular segment. So let's look at this segment here, right? I know I then have a BY and a BX coming in here. I've got the P hanging out on the end. All right, and then, so I have P here, so I have information on this one. Okay, and then we're gonna have to talk, and this is one of the things that you brought up, is the fact that it's got movement on a slant, doesn't it? All right. So it is limited on the slant, but it doesn't clearly have a motion that's free, for lack of a better term. Oh, this is a P. So this is 13.2, right? Okay. All right. So C is going to have both an X and a Y component to it.
Because it's a slit.
Well, because it's a slit on an angle, if the slit was vertical, then it would only have an X component. If the slit was horizontal, it would only have a Y component. But we have this angled slit. So let's go ahead, and this one I think I can work with. Why? Well, if I take a moment about B, what's going to disappear for me?
CX.
And you.
All right, so if I take a moment about B, CX and all of B is going to disappear, and I can solve for CY, can't I?
I don't think it gives us information, like the measurements on C. So we might have to take a moment at C. So it's gonna be-
Well, but we can figure out what those are,
So does it-
all right?
Let's try.
So we know we can figure, well, actually know that this is an F. So we'll have to use similar triangles. Right, and so if this is F here, and this is A, we know that this is 0.9. And this distance here is going to be 1.8. Right, and so then we're going to have a secondary smaller triangle. This is going to be 1.2. This is unknown, but this is still A. So that angle isn't changing. All right, so if we then have 1.2 times, let's see, so we can run this, can't we? So we have 1.2 is to 1.8 equals X is to 0.9. X is going to be what? What is it? 0.6? All right, and so we now know that distance. P is then going to be, assuming that's in the center, which it is because it's 0.9 on both sides. So we know the distance from here to here is then 0.3, and we found that this is then 0.6. So that means if this has to also be 0.6, doesn't it? Okay, so CY is going to be off by 1.2. You see what I did there? How are we doing, Dallas? Are we okay? All right, Ben, are we okay? All right, so let's go ahead then. We're going to take a moment about B. All right, and then we're going to have CY times 1.2, and that would be going counterclockwise, minus my 13.2 times 1.8. That's going to equal 0. So I believe we get CY 19.8. Anyone getting 19.8 for CY? Oh, you're telling me that's what you got. I thought you had a question. Do you have a question, Cameron?
Yeah. Weird.
See why have to do.
Okay, so if we're taking a moment about B, we need to look for anything that's a perpendicular force to B. So CY is going to be a perpendicular force to B. And so is P. All right. So we now have our CY. Can I get my BY now? Yeah. So we're gonna have BY plus CY minus 13.2 equals 0. All right, so BY is gonna come out as what? What is it?
-6.6,
Negative 6.6.
like pairing it to the other side.
Yeah, no, you're cool. I'm just checking, I'm looking at the answer. Negative 6.6 kilonewtons, but it's pointing down. So it's 6.6 kilonewtons pointing down. All right, so now we have a little bit more information, don't we? So BY should be going the other direction. And this is going to be 6.6. CY is still pointing up. All right, and so CY is then 19.8. All right. All right, so let's talk about CX is 2CY. Why would CX be 2CY? It must be that angle. All right, we also now know that PY over here, we now have information for, don't we? Okay, we know that this BY is 6.6. So we're able to start filling in information. Okay, so that's at an angle 2CX equals CY. Curious about where he got that from. All right, so let's go ahead. I'm hoping we can go after CX and BX from another route. We can go back to this one and we can get AY, can't we? Right? If we go back to this diagram. So if we now sum in the Y direction, we're going to have AY, which is pointing up, minus 6.6 minus 2.2. So AY is going to then equal 8.8 kilonewtons.
For CX, could you not use a triangle to find it?
Yeah. I'm thinking so. Okay, and they said I did it wrong. So we have 6.6 pointing down here.
Is it reversed on?
Yes, it is.
Or not?
So it's going to be going up here. Plus, so this ends up being 4.4.
Minus 4.4?
What's 6 months?
Yeah, minus 4.4. So this is coming down at 4.4. Okay, we're getting closer. Yeah, so I think what's going on with C is we know that angle, don't we? And that's what he's doing there. So let's take a moment and look at point C as if it is a point source. All right, we have CY and we have CX. Right. And you can think about it, those are going to make a triangle, aren't they? So we'll have CY, we will have CX, and then we will have our total force C. He looked at this in comparison with this is 0.6 and that is 1.2. So because of that, that means CY has to equal to CX if we look at it relative to the triangle, the triangle that it's forming. All right, so we can then go back because of that, we know CX is going to be half of CY. Did I write that right? No, I wrote this wrong. Oh, let's just set it up, Molly. 1.2.6, right? That's then going to equal CY divided by CX. So what do you get for CX? It's going to be 2CY.
Be 1/2 CY, wouldn't it?
Yeah. CY over
CX would be 2CY.
Yeah.
Cause the left side just goes to 2.
Okay.
Or it could be CY equals 2CX.
All right. So CY, I was right the first time, equals 2CX. We know what CY is. CY is 19. So half of that is going to be my CX. So what's CX going to be?
9.5. Wait, you said it was 19?
Well, yeah, we found CY
19.8.
19.8,
It's 9.9.
9.9.
Is it? Yes. When did you stop writing?
Okay. So let's go back up to here. CX is then going to be 9.9 kilonewtons. Now, can I solve for BX?
You read it.
Yes, no, not theoretically. We can now solve for BX.
Oh, yeah, it just,
Hopefully your work is much neater than this. All right, so that's going to be the negative BX plus 9.9 equals 0. So BX is then going to be 9.9 going in that direction. All right, cool. So this is now 9.9 going in that direction.
so now we can.
So yes, so now we can take a moment in order to we can take a moment about A or E in order then to get AX.
Is that going the other direction?
BX is going that way, so yeah, it's gonna go this way.
Wait, why would it go that way if what we found was a positive number? Wouldn't that mean that we drew?
Because the way I drew it over here was it's a negative, goes in the negative direction.
It's reacting. It's like you have a beat.
All right, so let's grab this guy here.
You know how it's drawn on this, remember, it was the opposite on that. Yeah, cause it's like when you got two forces going together,
So you flip.
on one it's going that way, on the other it's going that way.
Oh.
So, yeah. However it is on one, it's opposite on the other.
Okay.
Yes.
Okay, let's take a moment. Let's go ahead and take the moment about A. Right, we're gonna have to figure out some distances. No, we don't. We already know them. Moment about A equals 0, right? We know this distance here, we already found. That was the 1.2 distance, correct? And this distance here is 0.6, right?
Yes.
And E sub x is then gonna be off by 1.8. Right, because the 1.2 and the 0.6, if I'm taking the moment about A. All right, so this distance, overall distance here is gonna be 1.8. All right. So we are then going to have, if we're going about A, all right, so that's gonna be 9.9 times 1.2. Right, and then we're gonna have, that one's going clockwise, isn't it? Minus 6.6 times 0.6. All right, and then we're gonna have, let's see, what else do we know? That one's 2.2, so that's gonna be counterclockwise, isn't it? So this is gonna be then plus 1.8 times. Oh, wait, I'm looking at the wrong one, aren't I? EX is gonna be times the 1.8. All right, and then we need to look at that offset 0.9. Okay. So then we're gonna have the 2.2. And I think that's positive, is it?
Yeah.
Equals 0. So put that all in and we can solve for EX. Anyone online got it yet?
I think it's negative 5.5.
I'm hearing a negative 5.5. Is there a second?
I concur.
Okay, so EX should be pointing this way, 5.5. So can I now find AX? So if I sum in the X direction. Right, what are we gonna have? We're gonna have 9.9 minus 5.5. How did I write that? How did I draw it? I drew it positive. Plus AX equals 0. So AX is then gonna be negative 4.4 kilonewtons. Did I do that correctly? All right, so this is going this way, 4.4. Cool beans. Now, we're almost done because the only thing left to solve for is f of x, and we can go back to this one here because we just found EX was, which way was EX pointing? To the left, and it was 5.5.
Yes.
All right, so if we now sum in the X direction, we know this is negative 5.5 minus f of x equals 0. So f of x is then going to equal negative 5.5 kilonewtons. So this is actually going the other way, right? Yep, there you go. So now you solved the whole thing. All joints are solved.
I was just confused on like that slider joint. I thought it was a reaction force, so I counted it and started from the beginning, but I understand.
Okay. All right. So now that was a good problem to lead us into our frame problem. Did we find the reaction forces on our frame problem? What do you mean we found most of them?
Well. We found the left frame, a little bit parts of the left side.
Right.
Are we calling the forces after the joints react?
Yeah.
All right. So tell me what we found.
No, those are forces. Those are just forces.
Yeah. Similar reaction.
All right. Here's some notes. Okay. So it looks like we found BY and did we find BY and AX and BX? Is that correct?
Yes.
All right. So what do we know? Let's go ahead and give ourselves a free body diagram. And then did we show, oh, and then we need to solve for J with our internal forces, correct?
Yeah.
All right. And so I believe, did we leave off here? Right, and so A was 155. Here, B was 155. This was 62. Here, we're going to then have a CY and we are going to have a CX. And then here, we're going to have a DY. So is that where we left off?
Yes.
All right, let's go ahead and take a moment about C. Because then I can solve for dy. What I am looking at is, well, I guess we could solve for all of C, but our point J is here, isn't it? So if I cut it and I solve this side where dy is coming in, or going out, I should say, drawn the other direction. Right? Then we can figure out what our internal forces are. So let's go ahead and take a moment about C. All right, so what's going to affect C? Well, that 62 is going to affect C, isn't it? And it is off by 4 inches, and it is going clockwise. Did I do that correctly?
Yes.
All right, now the BX, that 155 here, this one isn't going to be affected. It's not going to be part of it. Why not? Okay, it's on the line of action, isn't it? So we're only going to have to find BY. BY is then off by 8 inches, or I shouldn't say BY. AX, I'm sorry. AX is off by 8 inches. All right, and so if we're here at C and we have AX going this way, we're going counterclockwise. So that's going to be plus 155 times 8. And then we're going to have D. I drew D going up, which is going to make it a clockwise motion. So we're going to have dy times 12. All right, go ahead and solve this then for dy. It should actually be pointing down. I drew it the wrong way.
Would you,
What's up?
on your notes on like when you previously did a little bit of it, You called it FED,
Okay.
the same, that's the same thing, right?
Yeah. So what did you come up with then for that?
Yeah, negative 82.67.
Anyone else get that?
Yes, yes.
Okay. Yeah, that'll work. Okay, negative 82, which means I drew it in the wrong direction, correct? It's actually going to be pointing down. So now we have the information to make our cut at J. J is given to us as where the cut is going to occur. All right, so this is my cut at J. Here, my FED is then equal to 82.6 pointing down. All right, so we are then going to have what three forces are happening on the inside?
Shear, axial, and moments.
Okay, so we're going to have a shear force. We're going to have an axial force. And we are going to have a moment. All right, so let's figure out what these are. And this is, my handwriting is horrible. This is 82.6. 82.7.
6, 7.
Okay, but we can round it to 82.7.
Yes.
All right.
The moment is the bending force, right? Or is it the?
No, the moment, the shear is the vertical force, right? And then you have the interior bending moment. So that you're looking at resistance, what, right? You're looking at it not bending, sort of like when it's embedded in a wall. All right, so let's go ahead. If we sum in our x direction, then our axial force for this is going to be 0. Okay? Our shear force is in the y direction. So then, oopsie, I don't know what I just did. Okay. So then we're going to have shear minus the 82.7 equals 0. So my shear force is drawn correctly, and it's going to then be 82.7. Are we in newtons, not kilonewtons? Pounds? Okay, we're in pounds. All right. Finally, we need to figure out our bending moment, don't we? All right, and so that is going to cause, the 82.7 is going to cause a clockwise moment, and it is off from J by 6 inches. So we can say our moments have to add up to 0. So we're going to have the moment on the inside minus the 82.7 times 6 equals 0. Was the 6, is that the right number? Yeah. So that's going to give me the moment on the inside of what?
And you're taking a moment at the breaking point?
Mhm.
Okay.
What'd you guys get?
496.
496?
0.2.
496.42? All right. This is in pounds, inches, which actually makes me nervous, but we'll leave it alone.
It's
That's
0.2.
what you're- Sorry?
Not 0.42.
Just 0.2.
All right, so your author has a tendency to leave things in pound inches. I would really like to divide that by 12 and have it in pound feet, just because that's a much more standard way we refer to moments. Okay, how are we doing? I got a shrug,
Static wise or life wise?
Yeah.
statics wise.
Oh,
So,
whatever.
I mean, I have no understanding. Wait, what is that number seem like crazy big?
Because it's in inches.
Because it's in inches.
Should be like
It's 41 foot pounds. Yeah.
Okay.
Yeah, it would be 41 foot-pounds. Yes.
Do we, like, are we able to, whatever we find it in as the first unit, are we able to just keep that unit? As the unit?
Right, yeah, you don't have to change units in this class, because your author doesn't change units. He's reporting in pound inches, which, as I said, is, in my opinion, it's wrong, but that's okay. So we'll follow the book because I don't wanna make your life difficult compared to what I want based on what the author wants. In the future, you might wanna divide that by 12, so it would be in feet pounds, because that's much more of a common measurement for us. I believe in solids, we usually record it in feet pounds in that book, Mechanics and Materials. All right.
Is that what it wanted to know?
Yeah.
What?
That's what it wanted to know?
Yeah, it wanted to know, so here, let's do a quick review because we did sort of dive into this problem and we're gonna need to understand this problem to move into the next section. All right, so what it wanted to do is it wanted us to find the interior forces. Internal forces, I'm sorry. Okay, so there are always, well, there's more than that, but we're focusing on 3 internal forces. So whenever you see the words internal forces, right? What we're gonna start by doing is you're gonna have to start by solving, for lack of a better word, solving your frame or whatever you're working with. Okay, then you're gonna want to cut it. When you cut it, and it doesn't matter which way you cut it, there are always 3 internal forces. All right, Ben? The 3 internal forces are then going to be an axial force. It's going to be a shear force. On your free diagram, your shear force is only going to have half an arrow associated with it. And then it's going to have a bending moment, or its resistance on the inside to actually bend. All right, if you think about it, if I'm hanging onto this pin and I put a force here, right? Interiorly, it's resisting actually bending, isn't it? So that is what we have. So if we let's look at one where we're just gonna cut it up, and then we'll move into the diagrams. All right. So let's say, and your author, I don't like the way the author teaches this. Just be honest. This is the only time I divert from him. Let's say this is say this is 20. Let's say this is 80. And we have a force. I probably shouldn't do it this way. Here, let's just redo this. We'll make each of these 50 and we'll put it in the middle. 50, 50, and we have a force, applied force, dead center of 100. Right, and we can call all of these pounds. All right, and we can say then this is then 10 feet. Okay. Let's say, for example, I want to cut this and you'll be told where you're gonna cut it. But let's go ahead and cut this at 5 feet. All right, and let's see what happens when we do that. All right, so we're gonna cut it at 5 feet. We can solve either side of it. It's not gonna make a difference. I want this work. There it goes. All right, but if we're looking at it, all right, this is then here at 50. There is an axial force here. There is a shear force here, and then there's gonna be a bending moment that's gonna be there, correct? It doesn't matter which side we solve for. We could solve for the other side, where we would have a cut. All right, and then this we said was 50. This was then going to be 100, right? And then once again, we have a shear, we have axial, and we have our bending moment. Oh, my shear is going the wrong direction.
They have to be on the same line of action to have the same braking values.
Yes. Well, they have to be part of the same piece. Does that make sense?
They have to be part of the same frame that you.
Right. The same piece of the frame. All right. So now we have two pieces. We can choose which one to solve. I think you can see if we sum in the x direction, it doesn't matter which one we work with. My axial force is going to be 0, isn't it? All right. If I sum in the y direction, then I'm going to have 50 minus my shear equals 0. So my shear is then going to equal, okay, so I drew my shears backwards. No, I'm okay. So my shear is going to be 50. If I look at it on this side and I sum in the y direction, right, then I'm going to have my shear is pointing up. Minus 100 pointing down, plus 50 is going to equal 0. So then my shear is going to be 100. So it's going to be 50. All right. You see, it didn't matter which one I solved for, did it? If we take the moment on the left-hand side, and the moment is always at the cut. All right. We're going to have the moment of cut, which I drew counterclockwise. Right. And then we're going to have the incoming moment from 50, which is going, I believe that's going clockwise. Is that correct? Yes. And it's off by 3. Equals 0. So here the moment of the cut equals 150. Okay. And that's going to be in pounds feet because I set up the units properly. Because I'm not a dinglebat like the author. All right. So if we look over here for the moment, 100 is going to go clockwise. I have the moment going counterclockwise is the way I drew it. 100, and that's then going to be off by 2, and that's negative, isn't it? What?
For that left side, that distance is 5 feet, right?
Oh, is it?
Yeah. So
Oh, sorry. I don't know why it became 3 in my brain.
You don't even, I don't think you declared a distance at which to do the cut.
Yeah, I did. I did. I said the cut's going to be at 5 feet. I don't know where 3 came from. So this needs to be 5. So this becomes 250. So then this is minus 100 times 5 plus, and then we're going to have 50 times 15. I got, it's going 10 to 100 and then another 5. And it's going counterclockwise. So this is going to give us minus 500 plus, and then I need 15 times 50. 750. 750? Perfect. Equals 0. So you'll notice my moment here is then, this is negative moment, it's going to be negative 250 LB B. So my moment here is then 250 LB feet. It didn't matter which side I solved. Okay. All right, now what the author likes to do, we're going to start talking, I'm going to teach this to you graphically. Okay, because the author goes, well, if I want to figure out what's happening across the beam, I then have to take a point there. And let's take a point here, and let's take a point here, and let's take a point here, and there. Because he doesn't believe that you have had calculus, to be very honest. All right, what? I don't know. But he honestly, truly doesn't believe you have calculus. So he will take a whole bunch of points along it. Instead, I want you to use your calculus, not in a scary way. Let's do a quick review. All right. So this is your calculus review, Calc 1. It depends. Some of you, it might have been a little while since you've done this. If I have X and Y and I say that X is here, or not X, but I've got a line here, Y equals 5, what's going to be the integral of that line?
The area under that point.
Area under the curve, what's it going to look like?
That will just be a rectangle.
The area will be a rectangle. What will the integral look like? If I have an expression Y equals 5X and I integrate it with respect to X, what do I get?
5 times X.
So it's going to look like this. It's going to be a straight line up, isn't it? Right? Where the slope on this line is then, this line can be described then as 5X, can't it? Let's take it one step further. All right? Let's integrate that one. So if I have a straight line, what's it going to turn into?
5x squared over 2.
5x over 2 squared, isn't it? So graphically, it's going to become a parabola, isn't it? Okay. So this is then y equals 5 halves x squared. But I want you to look at this. We go from horizontal line to a straight line, correct? To a y equals mx plus b line to a curve. Question, Kate? No, to stretch it. All right. What happens? Let's think about this in terms of, we're going to do shear and bending moment diagrams. Now, my attitude is use your calculus. The author's going to make you determine a whole bunch of little points. All right. And I think that is, I don't want to say it's a waste of time, but it's a waste of time. I don't know any other way to put it. Okay. So here is what you're going to do. And you can think of it, if we go back to this diagram here and say this is 50 and this is 50, right? And over here we have 100. You could do this probably in your head. At this point, right, we're going to have a shear of 50, aren't we? At this point, what are we going to have? A shear of 50. At this point, what are we going to have? Shear of 50. Then we hit this thing. So now we're going to have a negative shear, aren't we? Because now we're pushing down by 100. This here is a critical point. These are my critical points. Right? So I want you to draw your shear diagram right under. And what's happening? I'm going up by how much? 50. This is my next critical point. Now, I have to go down by how much? 100, right? Because when we find our shear, we're basically summing in the y direction. So here we're going to go down by 100. That then puts me at negative 50. All right, what happens at the far end? Goes back up to 0. This is my shear diagram. Okay. Now, and all we're doing is we're following what the forces are doing. Why are people logging in 30 minutes early to 2:32? Don't understand. All right, so this is what, by the way, on the edge, if we're on the end, right, we're going to have no shear and no bending moment, unless it's in a wall. All right. Okay, so your problems are going to start at 0 and end at 0. This is what the author doesn't seem to think you know. And that is that the shear is then the derivative of the bending moment with respect to x. Okay, they are related this way. So you can think of it, your bending moment, if you do separation of variables, is then going to be the integral of the shear. Okay, so what are we going to do now? We're going to do the same thing. I would tell you, now I'm going to draw my bending moment diagram. So here's my bending.
They're not connected though, right? They just happen to like be right on top of each other.
I'm going to connect them
Oh.
because I want to keep my critical point is going to be the same. If I have a horizontal line, that horizontal line is going to become a what? Horizontal line becomes a line at an angle, doesn't it? Diagonal line, that's a good word. I know this x is 10 and this x is 10. So what's the area under that curve? 500. So up here, we're going to be at 500. So this is going to go up to 500. All right. It is positive x. So it's going to then have a slope. This equation of this line is then going to be 50x. What's then going to happen? It's going to do what?
The opposite.
50x.
It's going to go down.
Negative.
This is then negative 50x. All right. So this is how I want you to do the bending moments and the shear diagrams. Your author will have you, literally, he will have you choose like 20 points. You put them in, you calculate it for each point, and then, but you'll end up with this anyway. Yes, Ben?
Is the next integral like a breaking point or something? It's gonna, like, if you do another integration.
No, if you do another integration of that, what are we going to have? We're going to have parabolas, aren't we?
What's the value of that, or does it know? Cause you know, like shear, And they do the integral of bending, and then what's the integral of bending?
It'll come to me in the middle of the night.
If there is one, I don't know.
No, there is one, because we've done it, haven't we? Not yet in solids?
Is it short for Portland?
Is it what?
Short for Portland?
Yeah.
That makes sense. Maybe not.
GTS it. Integral of bending. It's actually the, we then, okay, bending moment. No, this isn't telling us. The deflection. All right, so the integral of this is how much it's deflecting. Internal deflection, which we've done. Yeah,
I don't think we talked about the integral relationship.
no, I don't think we did either. But it's gonna be the internal deflection. All right. This one is pretty nice. Let's do one that's a little more complicated before we get into the ugly ones like your author likes to give you. Let's actually go ahead and walk through this one. So let's say we have 6 minutes. We can do it in 6 minutes. All right, we have a roller here. We have a pin connection here. Let's say we're going over 3 feet and we're coming down 20. We're going over 10 feet and we're coming down 40. And then we're going over another 3 feet and we're coming down. Well, that's just it. We'll just have 2 forces. All right, can I solve for my reaction forces? Absolutely, we better be able to. This one is going to have, we'll call this A. It's going to have an AY and it's going to have an AX. AX is going to be what? 0. This one's only going to have a BY associated with it. All right, so if I take the moment about A, what are we going to have? We're going to have -3 times 20, right? We are then going to have -13 times 40, and then we're going to have plus by times 16 equals 0. So what do you get for by? I made the problem up, so I have no idea.
580.
580. Oh, that's really high. Did you divide by 16?
Oh, no, sorry. 36.25.
Okay, I buy that one. What was it? 36.25. All right. Okay, now if I sum in my y direction,
We have to flip our BY though. It's a negative. Oh, wait, no, never mind. We're good.
we're gonna have AY -20 -40 plus 36.25 equals 0. So AY is gonna be what, 23.75? I do that right? I did that in my head. That's always dangerous.
Yes.
Okay, so we found our reaction forces like in 2 minutes because you guys are pros at these now. So what I would do is give yourself another free body diagram. This we found to be 23.75. We go over by 3 and this was 20. Yeah. We then head over by 10 and this here is 40. We then head over another 3. And here we then have a force of 36.25. Okay? So we get our basic forces. Now, let's go ahead then and do a shear diagram. We start by going up how much? 23.75. So we're going to go up 23.75. We're going to go over. This is a key point, critical point. This is another critical point. So then we're going to go over to here and we're going to drop down by 20. So now we are here at 3.75. We're going to head over to this critical point. Now what do I have to drop down by? 40, and that's going to then put me here at negative 36.25. It comes over and then it heads back up to 0, correct? Shear diagram, done. Bending moment diagram. I'll need some calculators run, because now the numbers aren't going to work in my head. This is 3, this is 10, and that is 3, correct? All right. So 3 times the 23.75 is what?
71.25.
All right, so I'm here at 71.25. That's going to go like that. All right, 10 times, that's going to be 37, isn't it? All right, so we're still going up, but we're going up at a different slope. All right, so this one is going up here. And this one here is then going to be 71 plus 37, 108. And then I need 36 times 3, and it better be close to 108. I'm doing things in my head though, so that's always bad. What is it?
36 times 3 is 108. Watch.
So that's what that bending moment diagram looks like. Okay. We're out of time. We're not out of this section, because we're going to have to talk about how we're going to deal with distributed forces and bending and shear moments. All right. Do your homework the way we just did this. Don't find every single little point. Just start a pile there. And I'll see you guys. We will have class on Wednesday. All are dismissed.
The exam.
I did take attendance at the beginning of class. What exam? Your exam is next week, right?
On Wednesday.
Wednesday of next week, correct?
Yeah, it's just like.
Yeah, it'll still be Wednesday of next week.
It's like we don't do anything. We have a fun product.
Let me
Yeah, or you just.
get those of you that came in late.
Okay.
Who came in late online? You post in the chat.
Think about reinforcing. Yeah.
Olivia. Jonathan.
Here.
Pardo. No, because there will be, well, it depends on where we get. So there will be some lecture between the 4th exam and the final. So you're guaranteed those problems. What's up?
She can go first.
Pretty sure, okay. I came in late, one, first thing, and then two, do we have oh, we were gonna have a quiz today, do we have a quiz on Wednesday, or is that?
I don't know. My mother-in-law died yesterday, so I'm like barely fresh. So What's up? It's not unexpected. My father-in-law died in September. They were married for 60 years.
Oh. So we were just-
So.
Yeah.
All right, awesome.
They close at 6, so it's like, well,